Hi, everyone. Welcome to the online causal inference seminar. Today, we have two speakers to present for half an hour. Our first speaker is Xinwei Shen from ETH Zurich. She will talk about causality-oriented robustness, exploiting data heterogeneity at different levels. For the Q&A, we have her collaborator, Armin Taib, as the moderator. Sorry, there's a typo. So the second speaker is Giulio Grossi from the University of Florence. He will be talking about SMAC, which is spatial matrix completion method. And his collaborator, our Georgia, will be handling questions for him. And today, as our Q&A moderator, we have Sarah. And Sarah, please. Feel free to introduce the Q&A process.
So if you have questions, please don't use the chat, use the Q&A functionality. And then the Q&A moderator, so Armin and Georgia, will be also trying to answer your questions by typing into the Q&A tool. But if there are other questions, we'll read them out at the end of the talk, or if there are very fast clarifying questions, hopefully actually those Armin and Georgia will be already able to do. But if there is still something that you want to ask, we can ask also the speakers during their talk.
Yeah, I think, Xinwei, the stage is yours.
Yeah. Okay. Thank you for the kind introduction and also for the invitation. It's my great honor to give this talk. So I'm going to talk about causality-oriented robustness, exploiting data heterogeneity at different levels. And this talk will be based on joint works with Peter Buhlmann from ETH Zurich, Armin Taib from University of Washington, Alexander Hanzi and Michael Law from ETH Zurich. So we're going to consider the regression setting with predictors X and response Y, and they follow a joint distribution P. And we denote the prediction model by f theta of X with parameter theta. So for example, it could be a linear model or a neural network. And in the classical statistical learning setting, we often assume the data is identically distributed. And so we focus mainly on the optimality of a prediction model for a fixed distribution. And we typically pick a loss function, and we want to minimize the expected loss, the risk, under this fixed distribution P. And the classical method is empirical risk minimization, or in the linear regression setting, it's ordinary least squares. And however, practice often deviates from what we typically assumed. And so here I'm going to give two scientific applications that I've been more or less working with. The first example is climate prediction under different climate change scenarios. And so according to IPCC report, Intergovernmental Panel on Climate Change report, there are 5 possible scenarios for the future, each corresponding to a different emission level or social economic changes. And so essentially it means different scenario has a different distribution, which we need to take into account when making predictions for the future climate. And the other example is in biology, where we're interested in modeling some genomic or proteomic responses, such as gene expression or protein expressions under certain perturbations. And each perturbation induces a different distribution for all the variables. And one particularly interesting question is to predict these responses under an unseen perturbation, such as a new drug combination. And so to tackle these distribution shifts, which are very common, one appealing mathematical notion is called distributional robustness. So instead of looking at a fixed distribution, we look at a class of distributions, this calligraphic P. And we look at the optimality of the worst case risk among this class of distributions. And so one nice framework is called distributionally robust optimization, which looks exactly at this formulation where the class is defined as the divergence or distance ball around a given distribution P0, which could be the training distribution. And however, one potential concern of this framework is when we have shifts in certain directions. So for example, here the blue dots might be the training distribution, and during test we may have distribution shifts along this direction. And in order to protect against all these possible distributions in using the DRIG framework, we would have to specify a relatively large delta. which will include way more distributions than necessary. And so then maybe we may end up with an overly conservative solution. And to alleviate this issue to a certain extent, existing literature has been looking at a causal perspective for dealing with distribution shifts. And so in particular, this means we're going to model the variables x, y using a causal framework, like a structural causal model. And this can be actually fairly general in the sense that, for example, in this graph structure, we could allow for both causal and anti-causal directions. So it means some of the covariates can be the ancestors of y, including the parents, and some other covariates can be the descendants of y, including the children. And of course, in general, we don't observe all the variables, so we should also allow for hidden confounders among all that could influence all of these observed variables. And also, we model distribution shifts as interventions on both observed or unobserved variables. And so under such a causal framework, we are trying to, so the key to achieve certain kind of robustness is to exploit heterogeneity in the observed data. And so in practice, data is often collected from multiple environments or sources. For example, if we use the E to denote this pair, X, Y, it can follow a different distribution for a different environment. And its calligraphic E is the set of all the observed environments. And so, for example, in the in the application that I mentioned earlier, these environments can be different climate change scenarios, or it can be different genetic perturbations, or in some clinical trials, these environments could be the hospitals. And so, in fact, the heterogeneity in the training data often occur at different levels. And the first level is in the first order moments. So it's mean shift. It means that different distributions may have different means. And the second level is the shift in the second order moments. So it's actually more general, saying that the distributions differ in their variances. So it could actually be the case where the different environments have the same mean, but they only differ in the variances. And the third level is the most general one, where the distributions in different environments can differ in different ways. So it could be the case where different environments have the same mean and variances, but the distributions really differ in quantiles or higher order moments. And so we see there's indeed different types of heterogeneity in the training data. And then our goal is to obtain a prediction model that is robust against future perturbations along the directions of the observed heterogeneity. And so we're going to make this more concrete in the following. So there is an excellent existing work called Anchor Regression by Dominic and co-authors that is trying to exploit the shifts in the conditional mean of all the variables given some anchor variable. And you could also think of it as an instrumental variable in some cases. And in the multi-environment setting, the anchor variable will be the environment index, so it corresponds to the mean shifts. And in this talk, under causal framework, we're going to discuss robust prediction by exploiting heterogeneity at different levels. And specifically, we'll first talk about how to exploit shifts in the variance to achieve potentially more robustness. And in the end, I will briefly talk about how to go beyond specific characteristics, but really exploit shifts in overall aspects of the distribution. So now the first work, Causality-oriented robustness, exploiting general additive interventions. And so this is the joint work with Peter Buhlmann and Armin Type. So the training data is assumed to be generated via a linear structural causal model. So the training data for different environments, they follow this model with the same adjacency matrix, this B star. And epsilon is the exogenous variables with potentially correlated components, which represent the hidden confounder between all the variables X and Y. And these delta E's are random variables that represent the additive interventions that generate variance shifts, in the sense that if we take the variance of ZE, then it can depend on different on the environment. So different environments can have different variance. And if you look at the last row of this system of equations, this gives us the structural equation for Y, where the coefficient B star represents the causal effects from the parents of Y to Y. And so this calligraphic E is a class of, it's a set of all the observed environments during training. And among those, we assume there is an observational environment indexed by 0 with no intervention. So it means delta 0 is equal to 0. And all the remaining environments are assumed to be interventional environments with non-zero interventions. So this is our training setup. And here's our test setup. So we copy the training setup here. And we assume the test data follow also a linear structural causal model with the same adjacency matrix. So this means the underlying causal mechanisms remains unchanged. And this makes a lot of sense in many applications. For example, this B star could encode some physical mechanism or some biological mechanism, which often is invariant. And we have a different intervention variable V. So this V is a random variable that represents a new intervention that could affect all of these variables. And it's in general different from any intervention variable during the training environments. So the goal is then to be robust against test distributions XV, YV for induced by this model for all V in a certain distribution class, which is to be specified and hopefully data dependent. And so here's our method, DRIG, distributional robustness via invariant gradients. So the population DRIG estimator for any gamma greater than or equal to 0 is defined as the minimizer of this regularized least squares formulation. So here we have the MSE, the mean squared error on the observational environment. And the regularization term is the weighted average of the differences of the MSE on any interventional environment and the observational environment. And so these omega E's are the convex weights and gamma is the regularization coefficient. And now let's explain why we call this DRIG. So when gamma tends to infinity, we're essentially only minimizing this regularization term. And so we can set its derivative to 0. And so the optimal B in this case satisfies what we call the gradient invariance condition. So it says that the average gradients across all the environments is equal to the gradient of the observational environment. And so then with a finite gamma, DRIG regularizes towards this gradient invariance. And later we're going to link this gradient invariance condition to both causality and robustness. So before that, let's first look at a few special cases of our estimator. So we copy the definition of the DRIG estimator here, and we look at a few values of gamma. So when gamma equals 0, we only have this term, which corresponds to OLS, ordinary least squares, with the observational data. And when gamma equals 1, and we take uniform weights, the DRIG estimator actually recovers OLS with the pooled data. And when gamma tends to infinity, which is kind of like the invariance gradient condition, it actually recovers the causal effects B star when it is identifiable. And so in this sense, DRIG interpolates between OLS and causal effects based on this finite gamma. And this is also why we call it causality-oriented robustness, because causality or the causal effects is just one extreme case of our estimator, and we're regularizing towards that direction. Right, and if we look at it from another perspective, we look at the special cases of DRIG when there are only mean shifts during training. So we recall the training SCM, the training model is given here, where mean shifts refer to the case where delta E's are deterministic. And when this is the case, the DRIG estimator for any gamma actually recovers the anchor regression with a categorical anchor E. And if you're not familiar with anchor regression, this is the formulation where intuitively, roughly speaking, we're trying to regularize such that the residual of the linear model is as uncorrelated with the anchor variable as possible. And so also it's straightforward to see then when gamma tends to infinity, both DRIG in this case and anchor regression recovers two-stage least squares or IV regression when it's well-defined. Right, and now let's look at the robustness guarantee for our method DRIG for a general gamma. And let's recall the test distribution here. So we have this model, structural causal model with a new intervention V. And this theorem tells us that the DRIG estimator for any gamma satisfies this. So the DRIG estimator is minimizing the worst case mean squared error among this class of variable V's. And so in words, DRIG prediction model is robust against perturbations in this class. And if we take a closer look at this class, so it consists of all the new interventions V with the second moments upper bounded by the weighted average of the second moments of the interventions during training up to a scaling. And so this scaling, this gamma, is exactly the coefficient, the regularization coefficient in our method. So it controls the strength of the perturbations that we're robust against. And the red part, this matrix, controls the directions of the perturbations. And now if you take a closer look at this red part, we'd like to point out here that the larger rank of this matrix means more directions that we're robust against. And so in the case of anchor regression that essentially exploits deterministic delta E's or mean shifts, so if delta E is deterministic, then each of these terms is just a rank 1 matrix. So the number of robust directions, the number of directions of perturbations that we're robust against, which is the rank of this matrix, is bounded by the number of terms that we sum up here. So that's the number of observational environments. So that means in order for anchor regression to achieve certain kind of robustness, we are more demanding in terms of the number of environments. And in contrast, DRIG can exploit general random delta E's. So this in general is a random vector. And so this is already the covariance matrix, which could already be full rank. And this means in principle, DRIG can be robust in all directions with 2 environments only. And we need 2 environments instead of 1 because we assumed that there is an observational environment. So delta 0 is always equal to 0. So we need at least 1 non-zero delta. And so DRIG, we can see in this sense that DRIG can exploit heterogeneity in the variance to protect against more perturbations, the perturbations in more directions. All right, and next, let's look at a real data example. It's a single cell data application where we observe gene expressions of 10 genes, and one of them is a response, and we have also 9 predictor genes. And for training, we have 10 training environments. One is observational environment without any intervention, and also we have 9 interventional environments. So on each of the interventional environment, one of the predictor gene is intervened on. So this brings us some heterogeneity within the training data that we're going to make use of. And so we have also 50 test environments that can be very different from the training environments due to some new interventions on unobserved genes. And the question we want to ask here is how robust our prediction model is on those test environments. And here are the results. So here we plot on the x-axis the regularization strength, so the coefficient gamma in our method. And on the y-axis, we show the worst case test MSE. So it's a maximum mean squared error among the 50 test environments. So that's an indicator for robustness. And so we can see that both DRIG and anchor regression with a larger gamma are doing more robust than these naive OLS estimators on observational data alone or the pooled data alone. And so DRIG with a larger gamma is doing more robust than anchor regression. And this is potentially because DRIG can also exploit the shift in the variance, which could occur in the training data in this case. So that's potentially why it can be more robust in the unseen test environments. And so this idea sounds promising, so we want to go a bit further to exploit shifts beyond the mean and variance. And so that's really the full distribution. And this brings us to the second part of the talk. So it's invariant. This work is called invariant probabilistic prediction. It's joint work with Alexander, Michael, and Peter. So here we consider a slightly more general setup than the previous one. So we don't assume linear structural causal model, but for each environment, we could actually allow for an arbitrary intervention on all the covariates X. So we denote it as of any function H of a given random variable, this noise variable. And the equation for y is also more general in the sense that g star can be a nonlinear function, and it can also take only a subset of x, so the parent of y, as its arguments. And the exogenous variable of y can be correlated with epsilon y due to some hidden confounding between x and y, and also because some of the x might be the children of y. And so now, because we want to exploit some shifts in the distribution, so instead of just predicting the conditional mean of y given x, now we need to have a distributional prediction. So we want to make a prediction for the full distribution. And this means the model, the prediction model now is no longer just a function of x, but a conditional distribution of y given x parameterized by theta. So one option is to model the density function or quantile function, or one could also build a generative model to describe this distribution. And in terms of the loss function, we use here the proper squaring rule, which is commonly used to assess how well a distribution fits the data. And so I think I don't have time to go into details of that method, but if you're interested, you can refer to this paper as one example of such methods. And we basically define the risk per environment as the expected negative score. And when the expected score is maximized, we recover the true distribution of y given x. And so the population version of IPP is defined as, again, a regularized formulation. So we first have the average risks across different environments, and the regularization term is trying to penalize a large variance of the risks for different environments. So intuitively, this means we want the risks of all the environments to be small, while the risks across different environments are not too different. And so this lambda is a tuning parameter. When lambda equals 0, we have the naive distributional regression estimator. And so we have some identification results for the method IPP. So the result is that we, under some conditions, IPP as gamma tends to infinity can recover this dual interventional distribution, where in this equation, we just plug in the value of x to be some fixed little x. And because the focus of this talk is prediction, so we directly jump into the results on exactly the same setting of the single cell data application. And so I hope this plot looks a bit familiar. We have still the results from anchor regression and DRIG here, and we add two more methods. So one is IPP, and the other one is the benchmark, which uses exactly the same models class, which is a neural network class in this case. So again, this is the regularization strength, and these are the worst case test MSE that indicates the robustness of the model on the test environments. So we can see IPP is the lowest curve, meaning that it's doing the most robust in the unseen environments. And there are two components that are playing a role here. One is that IPP is exploiting shifts in the full distribution rather than just the mean, as anchor regression does, or the variance as DRIG does. So that could bring in new robustness in the unseen environments. And the second component is, of course, IPP in this curve is using neural network model class, which brings some nonlinearity, which may fit the data better. And so we have this baseline method that uses the same model class that are doing much worse. So maybe this indicates that the first component, the fact that we're exploiting shifts in the general distribution, plays a more important role here. So to summarize, so in this talk, we discussed causality-oriented robust prediction by exploiting data heterogeneity at different levels. We, in particular, focus on the shifts in the variance and also the shift in the general aspect of the distribution. And as an outlook, it would be interesting to look at the robustness guarantee for finite perturbation strength in distributional or nonlinear settings. And we know when we are looking at distribution shifts for a non-parametric model class, we immediately have the extrapolation issue. And so we've made a little progress in this work. So if you're interested in nonlinear extrapolation, feel free to check out. And also similar ideas can be used to deal with the causal effects and identification by exploiting heterogeneity in distributions. So now in this talk, we just focus on the robust prediction part robust prediction on the distribution shifts, but one could also do causal effect estimation. And this is exactly what we're doing in our ongoing work, distributional instrumental variable regression. So if you are interested in this aspect, feel free to also reach out. All right, so with this, I will end my talk. Thanks for listening.
Okay, thank you very much, Xinwei. We already have some questions. I think Armin already answered a bit, but maybe we can also discuss it. So Dominic had a question, and the question was, the DRIG criterion can be potentially non-convex if the interventions are not additive, and if this is an issue in practical examples. So this is a question for Dominic, so he can also mute himself if necessary.
Yeah, thanks, Dominic, for the question. So it's non-convex not only when the interventions are non-additive. So yeah, let me see what Armin said. Yes, with additive intervention, it's usually convex, but with some weird gamma, it may also be non-convex, I think. So Armin, correct me if I'm wrong.
In finite samples, you mean?
I think even with general gamma, you need to make some assumptions on the distributions. So like the observational assumptions that we're making. And under that assumption in the population level, it's convex. But yes, in a finite sample case, it could be non-convex.
Oops.
Dominic
was...
Yes. So let's see.
But of course, if the interventions are non-additive, then basically we have no control at all. That's definitely true. And that's why I show here a real data example where we have no clue whether the interventions are indeed additive or not. So, but as shown in the result, it kind of works. So maybe this additive. We've also done some diagnosis actually, but not so rigorous ones, to see like whether we observe variance, increasing variance in the interventional environments compared to the observational environments. And that's indeed the case.
Okay.
So we have some kind of evidence to show there might be some additive interventions, but there might also be some non-additive ones.
Great, thanks.
Yep.
My internet froze for a second, but I heard your second part of the answer. So thanks.
Okay.
There is
so
another.
In the case of the, sorry, just the clarification. In case of the real data, it is like you can cast it as a convex program, and so you can solve it in closed form.
Okay.
It works out in that specific real data, but definitely not all the time.
Okay, great, thanks.
Okay, I just wanted to ask another question, which is in the Q&A right now, which says, could it be possible to put this in a Bayesian context due to dealing with the heterogeneity assessment, I think?
Yeah, I think that's a great point. But I'm not exactly sure, like by Bayesian context, do you mean, for example, like we have some prior knowledge on the weights of the environments? So because in our method here, we have the omegas. So these omegas are the kind of pre-specified weights that we assign to all the environments. And one could use some prior knowledge to assign different kinds of weights. That's one way. But we haven't really looked at this in a fully Bayesian context, but I think it's going to be interesting to look into that.
Okay, sounds good. I think so. I think if there are other questions, probably the people can reach out to Xinwei, Armin, and the other co-authors. And then I think now we're going to conclude the Q&A session for this talk, and we're going to move to the second talk,